Okay, so today we're starting a new chapter called Moments of Inertia. So we're going to use our techniques from finding the volumes of solids to now finding the moments of inertia of a solid. So you should be sort of familiar with moments of inertia from physics, but instead of simple systems from physics that you're looking at, these are going to be a bit more complicated. Okay, so firstly, what is the idea of moments of inertia? Well, let's say we have some sort of solid. Maybe it looks something like that. Okay, so it's like a 3D solid. We pick an axis through the solid, so the axis of rotation, and we rotate the solid around that axis. So given some sort of solid, whatever it might be, like the potato-looking solid here, we pick some axis through the solid. We're going to rotate the solid around that axis. And the question is, how difficult is it to rotate the solid around that axis? So question, how difficult is it to rotate the given solid around the given axis? Okay, so here we have the given solid and the given axis, which means those can change. So different solids will have different moments of inertia. For example, a cylinder and a cone, that will have different moments of inertia. And it also depends on the axis. You could have the axis going through the symmetry line of a cone, or it could go through the middle of a cone horizontally. That will also give you different moments of inertia. So different solids, for example, a cylinder and a cone. Okay, those will have different moments of inertia just because of the shape of them. But also choosing different axes will also give you different moments of inertia. For example, if you have the same solid, so a cylinder rotated around the central line, will give you some moments of inertia. If you pick a different axis with the same solid, you will get a different moment of inertia. So here, let's say the axis goes like this. Okay, so even with the same solid, a different axis will give you a different moment of inertia. And you can see roughly with the cone what we mean by this. So for the cone where the axis is going top to bottom like that, we see it's symmetric around that axis. Okay, so you just rotate it around that symmetry line. However, for the cone on the right, we see that there's a lot more mass at the bottom and very little mass at the top. So when you rotate that around the middle line, there's a lot of mass at the bottom that's going to be difficult to rotate around, but the top has very little mass, so that will be easier to rotate around. Now, you need to see, the combination of the two, how difficult is that going to be as a whole? Okay, so here we have different shapes. And here we have different axes, same shape. So the whole idea of this is different shapes will have different moments of inertia. Choosing different axes with the same shape will also have different moments of inertia based on how the mass is going to be moving around this axis. Okay, so let's look at the simplest case for this. Okay, so we have some origin point, O, and then some particle with mass m. So a point particle doesn't have any size, but it has a mass. And we want this to rotate around the origin. Yeah. So how difficult is it to take this point mass and move it around this origin at some radius r? Okay, so this is going to be I for moments of inertia. You should have seen that before. Is equal to r squared m. Sorry, half r squared m. Okay, so taking a particle, rotating it around, that r there shows how difficult it is to do that. Very large moments of inertia, very difficult to rotate around. very small moments of inertia, very easy to rotate around. So this gives us an actual number on how difficult it is to rotate these objects. So that's for the simplest case. Okay, we're not going to be looking at that. We're going to be looking at much more complicated cases. So more generally, we have the following. So more generally, let's say we have that potato shape we had last time. Okay, so some weird shape. We don't really worry about what it looks like for now, but some 3D shape, whatever it might be. We choose an axis. So let's say through there, and we're going to rotate the shape around that axis. What we're going to imagine is taking the shape and breaking it up into a lot of small masses, where we can use this simple case over here. So for the simple case, it's a very small mass going around the origin. Over here, we've got a much more complicated mass, like this, but we can imagine taking this and cutting it up into a lot of small pieces. So let's say we have a very small piece over here, very small cube. Okay, so it's a very tiny piece of the solid, and it's going to go around this axis. Okay, in a circle. So we pick a tiny little piece of the solid, and it's going to go around the axis like that, exactly how we did in this simple case. So a tiny little mass going around the origin. In the more general case, again, we pick a tiny little mass, and it's going to go around the axis. Okay, so we can look at the moments of inertia just for that little mass. What is that going to be? Well, if this little mass has mass dm, right? dm, small little piece, then we can write di is equal to r squared dm. Okay, same as we had before, where r is the radius from the origin. So here, this distance here. So the radius of that pink circle, that's going to be r. di, that's the moment of inertia for that little mass. And dm, that is the mass of that little piece. Okay, so that's just for that little piece, just the one piece. If we want the total moment of inertia, it's going to be the sum of all of the little pieces. So here we just chose one piece, and we got the little bit of moments of inertia. If we add this up for all of the pieces, we get the total moments of inertia. So I, that's the total moments of inertia. That's the integral of di. So that's going to be the integral of r squared dm. Okay, right, because we can't take a sum because it's infinitesimal pieces like we had with the Riemann sum. Right, you have the rectangles, you take the limit, and then the delta x became the dx. Okay, and then instead of adding up the delta x, you integrate up the dx. Okay, from going from discrete to continuous. So this gives us a nice formula for the general case. So if you want the moment of inertia for the total solid, this is going to be equal to the integral of r squared dm. Okay, so that's very general. Okay, so any question you get asked on moments of inertia, you can start with this and then get to the answer. Okay, but we're not going to do that. We're going to find specific formulae for specific cases. But if you forget them, you can always start from here. Okay, so you can think of this as like the first principles way of doing things. So you start from this equation, you can answer any of the questions, but we're going to find three cases, okay, 1D, 2D, and 3D, that will be much easier to work with. Okay, but again, if you forget all of that, you can always start from here. Okay, so first, let's look at the first case of a three-dimensional mass. Then we're going to look at the one-dimensional case and then the two-dimensional case. So case one, a 3D object. Okay, so what are we going to do? Well, we start off with the equation that's given and try to write it in a better way for us to do the calculation. So we're going to have I is equal to the integral of r squared dm. Yeah, so that's always our starting point. We always start with this equation. Now, what we're going to do is instead of integrating over dm, we want to integrate over x or over y or over z. We know how to do that. Integrating over dm, right, we don't know how to do that. So idea is to change the integration not over the mass, but over x, y, or z to integrate over the solid. So we want to change the integral from being an integral over the mass to being an integral over x, y, z. We know how to deal with that. Right, we know how to deal with those x, y, z integrals, whatever that might be. Okay, so the way we do that is by looking at the mass density of the shape. So we saw that end of last year, linear mass density. Now, in this case, it's going to be a volume mass density because it's a 3D shape. If you forgot that, go to your notes from last year where we covered the mass density in the net change theorem. Okay, so we've got some 3D shape again. It's going to have some total mass, whatever it might be. Let's say total mass m. Okay. If it has a total mass m and some volume v, then we can write the density, rho, as m over v, at the volume mass density. Now, this is a very special case. Okay, you've seen this in physics, hopefully, mass over volume, that's the mass density. This is if the density is constant. So you've got a fixed mass m, a fixed volume v, you take the quotient, that gives you a constant mass density. Okay, so this is for a constant density. So constant mass, constant volume. Constant density. Okay, what we're interested now is what happens if the density is changing from point to point. So it's not a uniform mass or constant mass density. It's going to be changing from point to point. So now we're going to have rho of x, y, and z. Okay, could depend on where you are. The density could depend on if you're in the middle of the solid or towards the edge of the solid, you're going to have a different density. So now it depends on x, y, and z. This is now going to be equal to not just the mass divided by the volume. Okay, that's just the average density or the constant density. It's going to be dm by dv. Okay. So think about that like your average velocity is your delta x over delta t, but your instantaneous velocity, that's dx by dt. Okay, so you must think of it like that. So for constant density, it's just m over v, like you would have delta x over delta t. The mass density where it changes from point to point, that will be dm by dv, like you would have dx by dt. Okay, so think of it in that way. Okay, and this is non-constant or non-uniform density. Non-constant or non-uniform density. Okay, and we'll look at examples with these two. So we're going to have solids with the constant density, solids with the non-constant density, and we need to know how to work with that. Yes, so that's number one and number two. Okay, so number one is pretty easy to do. We'll look at examples with that. Number two, it's a bit more difficult. So let's just have a look at that one. So for number two, we're going to have rho is equal to dm by dv. I'm not going to write the x, y, z, but you know it's a function of x, y, and z. We're going to rearrange this a little bit. So I'm going to multiply both sides by dv. That's going to give us dm is equal to rho dv. And again, this rho is not constant, but I'm not going to write the x, y, z. So now we have dm in terms of dv. So what we can do is take this equation, substitute it into what we had earlier there. I is the integral r squared dm. We can replace that dm now. So sub into I equals the integral r squared dm. So this now becomes I is equal to the integral of r squared. That stays. Then the dm, that becomes rho dv. Yeah. Now the next bit you're only going to see next year when you do multiple integrals. But what you would do is take this and write it as a triple integral r squared rho of x, y, z dx, dy, dz. Yeah. So beginning of next year, when you look at multivariable calculus and multiple integrals, you're going to be doing that on that right side there. So I'll just put a little box here. So this is for next year. At your math 238, you're going to be dealing with those more complicated examples. Now, for us, we're not going to be looking at triple integrals. We're going to be looking at much simpler problems, but the idea is the same. You're going to have some mass density rho, and you want to integrate that over the volume. Okay, but in our case, it won't be so difficult. Okay, but just make a note there, you will be seeing that beginning of next year. So that will be the math 238. Okay, so a little bit of warning of what's coming up next year. Okay. Next case we're going to look at is the one-dimensional case, much easier than 3D. So case 2 in 1 dimensions. Okay, so now we need to imagine a one-dimensional solid. Now that's quite easy to do. It just looks like this. Okay, it's just like a very thin cylinder. Okay, so it's got 1 dimension. You can just measure the length of this. Okay, so this is an example of a 1D solid. Okay, like a metal rod or a stick or something like that. Okay, it's one-dimensional. Yeah. And again, we're going to go through the same process. We're going to look at this in terms of the mass density and then figure out what that moment of inertia formula is going to look like. So exactly the same as what we did for this 3D case. Okay, so number 1, let's say we have a constant density. Okay, or you might hear this as uniform density. Okay, it all means the same thing. Constant density, uniform density, homogeneous density. You'll hear all of those words, they mean the same thing. So here, let's say this has a mass m and a length L. Okay, so 3D, you look at mass and volume because that's 3D. In 1D, it will be mass and length because it's one-dimensional. So here, rho, that's going to be the mass over length. Again, in 3D, you talk about volumes, so it's mass over volume. In 1D, you talk about mass over length, so it will be linear mass density rather than volume mass density. Linear mass density. Sometimes this is given a different name. So in 3D, we use rho. In 1D, you might see this as lambda. So just put a little star there. You might see different notations. Now, you could use rho for all of it, 1D, 2D, and 3D. That's perfectly fine. But for these specific cases, you will see different symbols used. So in 3D, you'll see rho being used. In 1D, you'll see lambda being used. And in 2D, you'll see sigma being used. Okay, but that's just notation. It means exactly the same thing. Okay, so constant density, constant mass, constant length, you just take the quotient, you get lambda. Okay, what happens if it's non-constant? So non-constant density or non-uniform densities, again, same thing. Okay, so again, now rho will depend on where you are in the solid. So in the 3D case, it will depend on x, y, and z because it's 3D. In 1D, it will depend on x, because it's one-dimensional. So we can write this as rho of x is dm by dl. Okay. Or you could write this as dm by dx. Okay, if you want to measure in terms of x. Okay, so that's rho of x. And again, you might see this as lambda. Okay, that's just notation. It's not anything different to what we have here with the rho. So again, you might see this differently as lambda x is dm by dx. Again, just notation. It's exactly the same as if you were to use the rho of x. Okay. So again, like we did last time, we've got this lambda is dm by dx. I can multiply both sides by the dx. That will give me lambda. That will give lambda dx is dm. And we're going to substitute this into the same equation we had before. So we're going to substitute into I equals the integral r squared dm. But now the dm is lambda dx, so we can just substitute that in. So that will be the integral of r squared lambda of x dx. Okay, so that's what we use in the one-dimensional case. Yeah. Any questions so far? No questions at all. All right. Last case, 2D. So case 1, we're not going to be looking at too much, but the case 2 and 3, that's where the majority of the problems are going to be. Okay, maybe bonus questions or extra exercises. I'll give you the 3D case to try. Okay, but 2 and 3, you have to know. That will definitely be tested. Case 1, that will be optional. Okay, so 2D solid. Let's imagine we have something like this. So it's a very thin disk. Okay, so it's very, very thin. So you can imagine this as just 2D. So very thin disk. It's approximately 2D. Right? So what we mean by that is the radius is much larger than the height. Okay, so we can approximate it as a 2D object. Okay, and again, we've got some axis going through this thing, rotates around. Okay, same idea as before. Okay, and we want to look at the equation in this specific case here. So there's the two cases. You can have a constant mass density or a changing mass density, non-uniform. We'll look at the two. So constant mass density. So again, we'll just call that rho, as we did for all of the other ones, and then I'll show you the notation for the special case. So this is just going to be m over a. So this is 2D, so we divide by the area. So we'll go through it one more time. In 3D, that's a volume, so it will be mass over volume. In 1D, it's one-dimensional, so it will be mass over the length. In 2D, that's two-dimensional, it will be mass over the area. Okay, please do not mix that up. Right, if you make a mistake on line 1 because you're dividing by the wrong thing, everything else is wrong from there. Okay, so again, 3D, volume mass density, 1D, linear mass density. In 2D, we have the area mass density, mass over the area. Yeah. And then the other notation that you might see, this could be written as sigma. Okay, you might see it like that. Again, just notation. It's nothing different from the previous equation. Okay, but that's very easy to deal with. The one that's a bit more difficult is when it's non-constant or non-uniform. So again, non-constant, non-uniform, that is where the mass will now, the density will change from point to point. So it depends on where you are. Okay, so here we're going to have rho of r. Okay, it could depend on where you are in this shape. Okay, that will be equal to not m over a, but it will be dm by dA. Yeah, same as we had before. Now we're going to look at a very special case of this 2D shapes. So something funny there. You've been talking the whole lecture. Well, what's going on? Hello? What's so important that you're talking about? Okay. One more interruption, I'll walk out. You can do this yourself. No, seriously. Everyone here, you're paying to be here. And then there's people that have no interest in being here. Okay. If I get one more interruption from anyone in this class, I'll walk out. You do this yourself. Okay. One more. Okay, so we have rho over r. That depends on where you are. That will be dm by dA. Okay, now we're going to look at a very special case of this. So not just any 2D shape, but more of this disk kind of shape. It's a bit easier to work with. Okay, the other examples you'll look at later on. For now, we'll look at the simple case like this. Okay, so very simple case for a disk where the mass density depends only on the radius. Yeah, so you've got some sort of disk like this. So top view looks like this. Okay, we've got some origin in the middle there. And then the mass density, wherever you are, only depends on the distance from the center. Okay, it doesn't depend on the angle going around, only the radius. So over here, at this radius, everything around that inner circle, that will have the same mass density. Okay, because it's on the same circle with that radius. If you're looking at another radius, again, the density all the way around for this other radius, that will also be the same. Okay, so the mass density only depends on where you are from the center. Okay, if you're right in the center, you have some mass density. If you're on the first circle, it will be some other mass density. If you're on the third circle going around there, that will be another mass density. Okay, it only depends on the distance from the center. So we can write rho of r. So not r vector, where it depends on the position, but just r, where it depends on the distance from the center. Okay, and again, this will be dm by dA. Okay, so now we made this assumption. What else can we use from this? Well, we know it's a circle. Okay, it's a circle there. And we know the area of a circle, right? Pi r squared. So we know that A, the area of whatever circle, whatever radius it is, that's going to be pi r squared. Okay, but what we want is dA. We don't want A, right? For that bottom part, we need to find dA. So we're going to take the differential on both sides. Okay, we did that last year under differentials. So dA, that's going to be 2 pi r dr. Right, we covered that last year under differentials. So we're going to take this, substitute it back inside there. Okay, so substitute back. So we end up with rho of r is equal to dm over 2 pi r dr. Okay. Now this 2 pi r dr, we're going to take over to the other side. So we're going to have rho of r times 2 pi r dr is dm, which is what we wanted. We want to take this and substitute it back into that original equation. Right, you know the I equals integral r squared dm. Okay, the one from right at the beginning. So we take the dm, exactly like we did in the first case and the second case, substitute it into the equation, and that gives us our integral. So I, that's going to be the integral of r squared times dm, but dm is all of that on the other side there. That's going to be rho of r 2 pi r dr. Now we've got an r squared and another r, so that will be r cubed. So this will be the integral 2 pi r cubed rho of r dr. Okay, and that is the third equation that we need. And you might see it, instead of rho, you might see it with the sigma, like we had here. Right, that different notation for the area mass density. So you might see this as I equals the integral 2 pi r cubed sigma of r dr. Again, this is just notation. It's exactly the same as what we had before. Okay, just notation. But it's important. You might see it written like that in the textbook or notes and so on. So it will be different. But if you want to use rho for everything, that's perfectly fine. If you want to use the rho, sigma, and lambda, that's fine as well. Okay, I'll leave that to you. Okay, any questions about these three derivations? So we've got the formula for the volume. We've got the formula for the rod, the one-dimensional case. And now we have the formula for the two-dimensional case. Any questions on those three? No. Okay, let's have a look at the examples. Just a note, the three equations and the original one will be given to you in the June test, the class test, and the final exam. So you're given those equations. However, you might be asked to derive them. Okay, so I'll give you I is the integral r squared dm. I'll give you a disk, and I'll say, what's the formula for the disk? Okay, but the equation's given to you, so you know what you need to get to, but you need to know the derivation. Okay, that might come up. Okay, again, class test, June test, final exam. You might see that. Okay, but these equations are given to you. You don't need to memorize them. Okay, so example number one. We're going to have a one-dimensional rod of constant mass density being rotated around some axis. So we've got some rod like that, again, one-dimensional, and we want to rotate around this axis. So I give you the shape, I give you the density, I give you the axis. What's the moment of inertia? So this is a constant mass, m, length L. Okay, so that's all the information you're given. Question, what is the moment of inertia around this given axis? And the axis could change. I could make the axis in the middle. I could make it 1/3 the way through, right? That can change. But in this case, we've got the axis at the end. What's the moment of inertia? Now, either you can start from that original equation, the r squared dm equation, or you could look at the formula sheet and find the one for linear mass density. Okay, that's up to you. If you want to start from the beginning or you want to start with the formula, right, that's up to you, whatever you prefer. Let's start off with the formula, the original one, and then work out what we need to do from there. So we're going to have I is equal to the integral r squared dm. Okay, so let's say we forgot the formulas and we don't know how to look for them. We're going to start from here. Now we know that this is a constant mass rod, metal rod, stick, whatever. What is dm going to be? Well, we know the density is constant. So we know lambda is going to be m over L. Yeah. Or we could write this as dm by dx. It's going to be the same because it's a constant density. So a little bit of rearranging here. We're going to have m over L dx is dm, which is what we need to put in the integral. So this is going to be the integral r squared m over L dx. M over L, that's a constant. We can take that out. And then we have the integral r squared dx. Okay, now we need to ask what are the bounds for this integral? And what do we do about the r? What's the radius going to be? So let's go back to this picture here. Remember, the whole idea was to cut this up into a lot of little parts. So let's show one of them here. So this little piece over there. This little piece is going to be rotated around, and it's going to have some radius from the axis to that little piece there. This is going to be the radius. Okay, from the axis to that little mass. So what is that radius in terms of x? X. From the axis to that piece, that distance is x. Right, you got your x and y axis here. So x and y. So the horizontal distance, that's x. So that pink radius there, that will also be x. Okay, like we did with the shell method and so on. So r equals x. Yeah, so we can substitute that in. That will be different if I move the axis, right? If you do the shell method around the y-axis or the shell method around x equals 1, you have to change the radius. Exactly the same in this case. What about the bounds? Well, we're integrating over x, so we're going to start from 0, and we're going to end at the length of the rod. So here we start at 0. The length is L, so we go from 0 to L. So we can substitute that now. So we have m over L, integral from 0 to L. R, that was just x. Okay, again, that will change later on. So this will just be x squared dx. Okay. Now we just do the integral. Yeah, very straightforward. So this is going to be m over L, square brackets. This will be 1/3 x cubed from 0 to L. The 0 is not going to do anything, so we can just put in the L. So this is going to end up being 1/3 m over L times L cubed. But L cubed over L, that's going to be L squared. So this is going to be 1/3 mL squared. Okay, so we end up with this. Okay, so that is the moment of inertia. If we take this rod and rotate it around that axis there. Now for homework, we're going to change the axis. What happens if you rotate around the middle? Okay, what is that going to be? So homework. Okay, so everything else is the same, uniform density, same length, same mass, but now the axis is going to be through the middle. So here we have x is 0, x is L, x and y. Now the radius is not going to be from x equals 0 anymore. the radius is going to be from the axis. So let's pick a little piece over here, for example. The radius will be this distance. Okay, so you need to do a little bit of working to find out what that radius is going to be. Okay, so that'll be for homework. Yep. And then you should get I is equal to 1 over 12 ml squared. Okay, so in the previous one, it was 1/3 ml squared. In this one, it is 1/12. And now from this, we can actually compare which one is more difficult to rotate. Remember the question right at the beginning, how difficult is it to rotate an object around an axis? In the first case, we got 1/3 in front. In the second case, we've got 1 over 12. Which one's easier? 1 over 12. That one's easier. Okay. Any questions on the example or the homework? No, all good. Okay. Yeah. The integral that you do is very, very similar to what we did with the shell method. Okay, so whatever techniques you did with the shell method, finding the radius and all of that, that applies over here. Okay, example 2. Okay, so now we're going to look at a 2D disk. So we've got some 2D disk like this. Okay, remember all of the 2D examples will be with a disk. Okay, we're not going to look at squares or anything more complicated. Okay, we've got some axis right through the middle. This is going to be a constant mass and a radius r. Okay. What's the moment of inertia? Again, I'm going to start off with the original formula and then work out what we need. But again, those 3 equations plus the original one, that will be provided. So this will be integral r squared dm. Okay, you can always start from the beginning. Okay, that's always possible. Now, what we want to do is try and rework this integral to match what we need for the disk, like we did earlier on. Okay, so we know that this disk has some area A. Pi r squared. Okay. Then we need dA, right, for that substitution. So dA, that's going to be 2 pi r dr. Okay, what about the mass density? That was that sigma. That was m over A. And that's also the dm by dA. Right, because it's constant, those two are going to be equal. Okay, so we have mass over the area. That is going to be pi r squared. That will be dm over dA, but we have that on the side there. That's going to be 2 pi r dr. Okay. Anyone lost with that? Okay. So we can substitute now. So this will be the integral r squared. Then that density, the dm by dA. dA. Right, this was that sigma that we called the dm by dA. Okay, so substituting what we have in that top right there, this is going to be integral r squared, dm by dA. We've got that on the side there. That's going to be m over pi r squared. Okay, because it has the radius capital R. Okay, times 2 pi r dr from that right-hand side there. Okay, so the pi at the top there, pi at the bottom, that's going to cancel. We've got a 2, we can take that out. And the m, that's a constant, we can take that out. So this is going to be 2m over r squared. Integral. What about the bounds now? So we've done all the substitution. the bounds will be in terms of the radius. So we're going to start at the center that has radius 0, and we're going to go all the way out to the end where radius is capital R. So we're going to go from radius is 0 to radius is capital R. Okay, so that's the bounds. We've simplified that inside bit, so that will just become R cubed dr. Okay, the constants we took out, R squared and R, that will become R cubed. So that will be 2m over R squared. Integrating this, very easy, 1 over 4 R to the 4. R to the 4. Then we substitute 0 to R. So this will become 2m over R squared, 1 over 4 R to the 4. Okay, that's after substituting. Now, 2 over 4, that's going to be a half. The m can go in front there. R to the 4 over R squared, that will just be a R squared. And we're done. Okay, pretty straightforward. Okay, so again, you didn't need to start from that beginning there. But if you don't know what to do, you can always start from the beginning. You could skip right to here. Okay, where you substitute the sigma. Okay, like we had before. Okay, so that is for a uniform mass disk. What happens if it's a non-uniform mass disk? What do we get? So next example, example 3. Okay, so same setup. We got the disk. We got the axis going through it. We want to rotate the disk around the axis. But now, instead of having a uniform mass, it now has a non-uniform mass, which means the dm by dA is not going to be constant anymore. So previously it was constant. It was the m over the pi r squared. Now this is going to depend on the radius. So this will be sigma of r, not constant. So the sigma is given to us, so that will be sigma of r is equal to a capital R minus little r. Okay, and we can see now the mass density depends on the radius. It's no longer constant. Okay, so let's work it out. So we're going to have, let's go back here, dm by dA is equal to the sigma of r, which is given. We can take the dA over to the other side. So we've got dm is sigma of r dA. Okay, and we've done this before. dA, that was the 2 pi r dr. Okay, and that dm is what we're going to substitute into that other formula. Okay, so we're going to have I is equal to the integral of r squared dm. And we just worked out dm. We've got that over there. So this is going to be the integral of 2 pi r cubed. Okay, r squared and r, that will be r cubed. Sigma of r dr. Okay, which is exactly what we got before. So this is just rederiving what we did earlier. Now the sigma of r, that's given to us, so we can substitute. So that is the a capital R minus little r. Okay, we can substitute that in now. Okay, 2 pi, that's a constant. We can take that out. Integral of r cubed, and then we've got the a capital R minus little r dr. Okay, what about the bounds? Well, same as before, you go from the center of the circle out to the end. So the bounds go from 0 to r. Okay, a is a constant. We can take that out. So this will be 2 pi a. Integral from 0 to r. The r cubed, we can distribute inside. dr. Okay, and then at this point, it's just normal integration. There's nothing too crazy there. Okay, so we've got 2 pi a r cubed. That's going to be 1 over 4 r to the 4 minus 1 over 5 r to the 5. Okay, and then we can substitute. So this will be 2 pi a. Okay, if we put in 0, we get 0, so we can ignore that one. Putting in the capital R there, we're going to get 1/4 r to the 5 minus 1/5 r to the 5. Okay. R to the 5, that's a constant. Okay, we can just take that out. Then we have 1/4 minus 1/5. So that's going to be 2 pi a r to the 5. And then 1/4 minus 1/5, that's 1 over 20. So we end up with pi over 10 a r to the 5. Yeah. So that will be the moments of inertia for this disk. Okay, then homework. Okay, so we're given the mass density. That was the sigma of R. Okay, so we're given the mass density. For homework, find the total mass. Yeah, and then little hint there. Remember, sigma was the dm by dA. Okay, so find the total mass m. Okay, any questions on this example? All good. And the homework, any issues? Okay. Then one more problem. So this will be a bonus problem for you to try. I always give you the bonus stuff. First one to come to my office with the correct solution, you get extra 5 for the next quiz. So it's a bit more difficult, but you can do it. So we have a cone like this. It's being rotated around the symmetry axis down the middle. Okay, it's being rotated around. It has base radius capital R. Mass m. A constant, so it's a uniform solid, so constant density. Height h. Show that I is equal to 3 over 10 mr squared. Yeah. So we want to find the moments of inertia for this. Okay. So this is an example of the 3D case that we looked at earlier. But instead of integrating over the volume, you're going to have to use like the disk method, washer method, or shell method to do that integral. I'm not telling you which one, that will give it away, but it's going to be one of those. Okay, any questions about this? No. Okay, yeah. First one to show me the working in my office, you get your extra 5 marks. Okay, so it will be the 5 out of the total 20. Right, 10 MCQ, 10 written, plus 5 onto that. Okay. Any questions before we go? All good. Okay, so I'll be in my office. Let's see who the first one is.